All right, we're on lesson 6 practice of Algebra 1, Illustrative Mathematics by Imagine Learning. This is on page 324 of your workbook, and there are 6 questions on homework. Yeah, so I need to adjust this up here. Okay, so the first one says the two graphs show models characterized by exponential decay. Remember that if it says exponential decay, it means that it's going down by the same rate of decrease, the same common factor, the same depreciation rate. And notice we've got two different functions. We've got a red that starts here, or call it the triangles, the red, whatever you want to call it. And then we've got a circles that starts here and goes down. So one is the triangles, one is the circles, one is the red, one is the blue, one is the one that starts higher, however you want to say it. It says which algae bloom covered a larger area when the chemicals were applied. That's the beginning, the initial, and explain how you know. So obviously this yellow one, this triangle one, the one that starts at 500. So let's go type in a little response here. Remember, your words do not need to be exactly my words. And so we can say the one with the starting point, the vertical intercept of 0, 500, or the one that starts with 500, covered a larger area, or the triangles, however you want to say it, right? And then how do you know? Because 500 is a larger number than 200, the starting point of the circles one, the blue one. Okay, so type that your response in your own words. Which algae population is decreasing more rapidly? Also, the triangles, or the one that starts at 500 is decreasing more rapidly. And you could say this for a couple reasons. You could say, I see that it starts higher and goes down much faster. I actually did the calculation and I can see that it went down by this factor compared to the other factor. There's a couple different ways you can do it. I see it jumps down much faster. It's steeper. I don't know. However you want to phrase this for your wording on how the 500 is jumping down way faster, it's steeper than the one with the 200. Okay, a medicine is applied to burn on a patient's arm. The area of the burn is equal to centimeters, decreases exponentially and is shown on the graph. What fraction of the burn area remains each week? So we're going to look at these first two input-output pairs on the graph. I'm going to go ahead and label them. For example, 0, 8 is our starting point there. And then 1, 6 is our second point. At least those two are on corners, so that I can look at those two outputs and divide and get the fraction that is our common factor. So we would say 6 divided by 8 is 3/4, or you could also divide those on a calculator and get 0.75. This is how much is remaining each week. Write an equation that represents the area of the burn after weeks. So remember that our equations always begin with the initial value 8 multiplied by the remaining factor, power of t time. How are you doing on writing those equations? What's the area of the burn after 7 weeks? You're going to go ahead and grab your calculator and plug in 7 for the time and see what you get. All right, and then you can compare your answer in class and check your teacher to see how much. It says to round to 3 decimal places. Be careful with that answer. The area of this sheet of paper is 100 square inches. Write an equation that gives the area So area begins with 100 square inches of sheet, and it is being folded in half. So my multiplier is a half, n times. So repeatedly to the power of n. You go do part B the same way. What's this one starting with in square inches? If this one's folded into thirds, what's the factor going to be? So what's it starting with? What's the factor going to be? Repeatedly n times. Are the areas of the two sheets of paper ever the same after being folded n times? I want you to picture that a graph that starts at 100 and goes down by half, 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 half. It's going to get infinitesimally close to the zero, but never touch. And then I want you to picture a graph that starts at 200 and goes down a third, a third, a third. That eventually these are going to like come together and get infinitesimally close to zero. So are they ever going to be the same? They are both approaching zero. Let's see. Where's my text box? You're going to answer this in your own opinion. Like, yes, they're both approaching zero. I think that they will end up being the same. Or is your opinion that no, they are not ever going to be the same because the half and the third are never going to land on the same exacts? Like, literally, what is your opinion on this response? And make sure you support it with some sort of an explanation. Okay, the graphs show the amounts of medicine in two patients after receiving injections. Here in this graph, one equation that gives the amount of medicine in milligrams is given here. And so how can I tell which one this is? Well, here's 100, 200, 300. So this is going to be the blue one. Let me go ahead and change this color. What could the equation for the amount of medicine for patient be? So if the blue one was starting at 300, then the red one is starting at, you got it, 200. So it's got to be one of these. Does that one look like it's going down to a remaining 7/10 or remaining 3/10 of itself? So you're choosing between C and D to get that answer. What do you think? And then we'll go over the answers in class. Select all equations that are equivalent to 3 to the 8th. I think we've done this one before where I'd like you to plug this one into the calculator and see what it gives you as a simplified output, but then go ahead and use your simplification exponent rules to see. So like this one's going to be the add rule, right? Add those exponents. What's that equivalent to? Do they match? This one's also going to be the add rule. Add those exponents. What's it going to be equivalent to? Do they match? This one, when we're dividing, is going to be the subtract rule. Can you subtract these and see which one is equivalent and which one is going to match? Subtract the exponents, top minus bottom. And finally, this one's going to be the multiply rule. You guys are exponent rule machines at this point. And so you can go ahead and apply those. Is it A or B? Is it C or D? Is it E or F? And then we'll go over those responses in class. Finally, on number 6, technology is required. So please go search up desmos.com graphing calculator. Once you get to the Desmos graphing calculator, you're going to click on the little plus sign and insert a table. And this is how you put in all the dots from this right here. So enter all those X and Y values right there into the table. Notice the X values are on top, the Y values are on the bottom. Now, after you input those values, your graph might look something like this. Oh, I've got this beautiful table input. Oh my gosh, where's my graph? Remember how we talked about in previous lessons, the window is very important. I'm too zoomed out to even see my first dot. I've got to adjust my window so I can actually see the points on my graph. There's one way to do it. You can zoom in and out with your mouse, or you can go up here to this wrench and give it an X and a y-axis boundaries from where to where, from where to where, and then we can see our graph more easily. So use the wrench or zoom in and out with your mouse. Now our job is to get an equation of a line of best fit. So I'm going to mess around with some equations. Notice we've got a decreasing set of dots, more or less. So I'm going to start by typing in just some random slope, like -2x. And look how my graph is way down here because it's going through the origin. So let's give it a y-intercept of something above here. If I do +30, it's way too low. If I do +40, maybe that's good. Maybe it's a little bit too high. So let's try, I don't know, 35. Let's just throw that in the middle and see how it looks. Then I notice my slope's a little bit too steep, but it is going down, so that's cool. So let's try a -1 slope. Uh, let's try 1.5. So notice how I'm just experimenting where, how can I get this to be kind of like there, like right in the middle? And look, close enough. Now, is there a way with a more advanced calculator to actually let the calculator calculate this line of best fit? Yes, but we don't have that advanced calculator in this class. So just using Desmos, I was able to do a really quick guess and check, adjust it around to get my line of best fit. And so now I go back here to the equation and I would type that. I'm sorry, text box. And I'm going to type y equals -1.1 plus 37, or literally whatever you got that was close to that you thought looked good. I'm going to go ahead and screenshot this in as my work so you guys can see it. All right. Great job on your homework. We are done.